Good morning. I am Yann Alibert, and I will discuss today end-to-end planet formation models. So the title of the talk is From This to Planetary System, End-to-End Models and Population Synthesis. So I will share my screen so that you can see the slides. I think I will stop my video, share screen here, play, and I will just check on the second computer if it works. Yes, okay. Okay, so this presentation, as I said, will be devoted to from this to planetary system, end-to-end models and population synthesis. And this is some work, I will present some work that has been developed at the University of Bern in the Theoretical Astrophysics and Planetary Science group, which is part of the NCCR Planetes. And I would like to already acknowledge the work of two people, Christophe Mordassini and Alexandre Msenebert, who really helped me a lot in doing this presentation. So, okay, so this is the outlines of the talk. I will first recap rapidly what is the co-accretion model, in particular the planetesimal-based co-accretion model that I will show and use later. Then I will present the end-to-end models of planetary system formation that we have been developing since the two last decades in Bern. And then I will use this model to compare the prediction from the models to the data we have on extrasolar planets and on the architecture of planetary systems. So let's start with the co-accretion model. So I will be relatively short on this one. So just to set the landscape, so we know that planets are believed to form as a byproduct of the stellar formation process. And the stellar formation process happens in what we call giant molecular clouds. So you have here one image of such a cloud. And then when we have some star-forming region, when we have a star that forms, we know that by the virtue of angular momentum conservation, there is formation of what is called a protoplanetary disk, which is a disk-like structure, which is made of mainly gas and some solids. So just to give order of magnitude, we have around 1% solids and 99% of gas. Then these disks are typically a few hundreds of AU in size, and they live a few million years. And then by some processes that we don't completely understand, we have formation of a planetary system. And then all the game that we are playing here is to try to understand how we go from a protoplanetary disk to a planetary system. So now there are basically two kind of models in order to try to understand the formation of planetary system. One is top-down and one is bottom-up. So in the top-down model, you start with a protoplanetary disk, and then there is some global instability that leads to a formation of planets. So this model, which is called the gravitational instability or disk instability model, has been studied for quite some time, and it may lead to a formation of massive gas giants, in particular in the outer region of a protoplanetary disk. But it's probably difficult to understand how this could lead to a formation of small mass planets like the Earth. The other class of model is the bottom-up model, so which is the one that we will use today. It is called the co-accretion model. So in this model, you start from small dust, some presolar grains and small dust, and then this dust agglomerates to form a planetary core, which ultimately may lead to a formation of a planet. So this bottom-up approach, so we start from small and we go to larger sizes, is in general named the co-accretion model. Now, to go a little bit more in the details, so how does this co-accretion model works? At least, how do we believe that it works? We start again from a protoplanetary disk, so again on the left, and then we have a formation of a planet or gas giant planet in two steps. In the first step, so on the left of the central diagram, you have formation of a core by accretion of solids. And I will come back later on, give a few words on what are these solids. So formation of a core by solid accretion, and then when the core has a mass that is beyond what is called the critical mass, gas accretion starts to operate in an accelerating way, in a runaway fashion, and this leads to the formation of a gas giant. So because the gas that is accreted to form a planet comes from the protoplanetary disk, so from the gas of a protoplanetary disk, then we have at this point, we see that there are two main issues potentially. The first one is that there need to be enough solids in order to reach a critical core mass, which is typically of the order of 10 Earth masses. So there needs to be enough solids. And the second, so this is a mass issue potentially. And then we may have a timescale issue because the accretion of gas should operate before the gas disk has disappeared. And as we have seen before, a protoplanetary disk has a typical lifetime that is of the order of a few million years. So the critical core mass must be reached before a few million years before the gas disk has disappeared. So we have on one side, we need to have enough mass, but also we need that this mass is collected on fast enough in a few million years. So when there is enough mass and the mass is collected rapidly enough, then we may form a gas giant. Now, in the second case where there is enough mass, but maybe this mass is collected on a longer time scale, so longer than the disk lifetime, or on a time scale that is similar to the disk lifetime, then the critical core is reached at a time when there is not a lot of gas in the protoplanetary disk, and this could lead to the formation of a planet that is core-dominated, like maybe the ice giants in the solar system. Now, the third case is that when there is not enough mass to reach the critical core mass, then in this case, we may end up with a planet that is similar to the Earth or terrestrial planets. So a planet that is completely dominated by the core and there is only a tiny gas envelope. Now, I've mentioned that one key element in the core accretion model is the accretion of solids. So now in the core accretion models, there are basically two subclasses of model, planetesimal-based models or pebble-based models. So these two models differ in the way actually we understand the efficiency of a transition from pebble to planetesimals. So the idea behind these two classes of model is that we start with some dust that you see on the top of the diagram, and then the dust collide with a particle of dust, and then this can form what we call pebbles, so which are particles that are a few centimeters in size. So in general, they are actually defined by their Stokes number. So their Stokes number should be around 0.1, just to give an order of magnitude. So this corresponds to particles that are around a few centimeters in size. And then these pebbles may interact with each other, and some of them can form planetesimals. So the transition from pebble to planetesimals actually involves some collective effect, which is known as the streaming instability, but I will not enter into the details. But basically, in the planetesimal-based and the pebble-based models, the sequence is similar. You start from dust, then you form pebbles, then you form planetesimals. But the main difference between these two models is what is the assumed efficiency of conversion of pebbles to our planetesimals. So in the planetesimal-based model, it is assumed that the transition or the conversion from pebbles to planetesimal has a very high efficiency. So it means that a lot of mass is in the form of planetesimals. Planetesimals being, in this case, bodies that have a size around a few hundred meters up to 300 kilometers. But what is important is that their Stokes number is much larger than the one of pebbles, and so their interaction with the gas is much weaker. In the pebble-based model, on the opposite, it is assumed that the conversion of pebbles to planetesimals has a low efficiency, which means that the majority of the mass is in pebbles. Again, pebbles being particles that are highly coupled with the gas with a Stokes number around 0.1. So in what will follow, I will assume, and I will only discuss the planetesimal-based formation models, and then I will try to see what are the predictions of this kind of models in terms of, in particular, extrasolar planets. I will not mention pebble-based models, which should be the topic of another lecture. So now let's move to the end-to-end models of planetary system formation. So I will start with some cartoon that tries to explain what are the main physical processes that are included in the models that I will show in a minute. So here you have seen from the edge, you have a sketch of the formation of a planetary system where you have two planets that will form, so depicted here by the Earth and Jupiter. We have the central star that is in the center of the disk. And so for all what I will show today, I will assume that the mass of the star is one solar mass. Okay, so I will not discuss the formation of planetary system around lower mass stars or higher mass stars actually, which is something that is very interesting, but that I will not address today. So then we have on this sketch also, we see from the edge the protoplanetary disk. So the scale height of the disk increase when we go out far from the star. And in this disk, as we have said already, there is gas and there are solids. So the solids are depicted by these round particles that look like asteroids. So there are different physical processes that are included in the model that I will show. And the first most important process is that we compute the accretion of solids. This is especially important for the core accretion model because, as we have seen at the beginning, in the core accretion model, the first step is to build a planetary core. So, and this results from the accretion of solids. So we compute the accretion of solids by forming planets. But we also compute the accretion of gas by the planets, in particular when planets they are beyond the critical mass. So you have seen on the animation that the gas planets, so Jupiter in this case, first grew in radius and then contracted. Okay, so now this is just a visualization of the evolution of the radius of a planet that will reach a critical core mass. So the radius of a planet will increase in the first step, and then at some point it will decrease because at this stage the accretion of gas starts to be very large, larger than that can be delivered by the protoplanetary disk, and then the planet starts to contract. Now, if we look at the evolution of the mass of the planet as a function of time, so there is a sketch that is shown on the screen here. And you have typically different phases, but what is important is that the mass of the planet always increases. So contrary to the radius, where there is first increase of a radius, then a collapse, then when we look at the mass, there are different phases, but then the mass always increases in this case. And then the evolution of the mass that we see here is typical of the formation of a planet like Jupiter. So first, very rapid growth up to around 10 Earth masses, then a slower growth for a couple of million years, and then again, rapid growth when the planet reaches the critical mass. So in order to compute this, I will give some more details later, but basically what we do is that we solve the internal structure equation to compute the internal structure of the gas envelope of the planet. So also something that is very important is that we include the computation of the excitation of solids, planetesimals in this case. So planetesimals, they are excited by mutual interaction between themselves and also by the interaction between forming planets and planetesimals. So basically forming planets increase the eccentricity and inclination of planetesimals. But there is another effect that is important. It's the fact that gas drag, which is the interaction between the gas disk and the solids in the disk, tends to decrease the excitation and eccentricity. So computing this excitation and eccentricity of planetesimals is very important because the rate of accretion of solids depends strongly on this E and I of planetesimals. So this has to be computed in a self-consistent way. We also include in some models the gas drag that gives so radial drift of planetesimals, which is especially important for small mass planetesimals, but what I will show later does not include this thing. Then we also include the angular momentum exchange between the protoplanetary disk and the forming planets. So angular momentum exchange has two consequences. The first one is to damp the eccentricity and inclination of planets. So angular momentum exchange put planets in general on quasi-circular orbits. And the second effect is that angular momentum exchange lead to migration of planets. Migration can be outwards or inwards depending on the thermodynamical condition in the protoplanetary disk, but also depending on the mass of the planets. We also include the interaction between forming planets, which is just computed by a normal n-body. And finally, we include the effect of the fact that the disk inner radius is not the same for all the protoplanetary disk because of probability truncation by magnetic field. And finally, we can also include the irradiation from the star, which modify the thermodynamics inside the protoplanetary disk with some effect on all the other processes. So what is important is that what we try to do is that we try to have all these processes that are computed in a relatively simple way. So we don't use any multi-D model here. For example, the gas disk is a 1+1D model, but we try to have all these processes included in a self-consistent way. So this is the way we can understand the formation model. Now, if we go to more details, so this is a very complicated diagram that is an extract from the paper by Alexander and Yann Alibert et al., which is in review. So this diagram that you see on the top is a summary of all the basically the basic physical classes of processes that we include in the models. So they are depicted in different colors. In blue, you have the processes that are related to the gas disk. In green, we have the processes that are important during the formation phase of the planet, so until the gas disk has disappeared. And then in red, we have the effects that are important when the gas disk has disappeared and during the evolution phase of the planet. So between a few million years up to a few billion years when we observe the planet. And so the philosophy of all these models the models we have developed is that they are based on standard models, low dimensional and static, but they are all coupled. And so each of the box that you see in the diagram, again, it represents some physics that is including in the model. And all the arrows that you see, they show how some quantity computed by one subpart of a model have an influence on some other part of a model. So, for example, if we take a closer look to the blue boxes, which are important for when we have a gas disk, so that's during the formation. So we compute the radial structure of the disk, but the radial structure of the disk has an influence on the disk of solids because of gas drag. But it also has some influence on the accretion rate of gas onto the planet, and so finally on the mass of the envelope of the planet. So just to give just a list of a rapid list of the different processes that we include. So in terms of the disk, we have 1D axisymmetric disk model. So it's an alpha disk model, and we assume that alpha is constant. And we also include the photoevaporation of the disk. So basically, this is based on the Lindelbell and Pringle ID approach of the alpha disk. For the planetesimals, we treat them not as individual particles, but as kind of a fluid. So they are treated as a surface density, where we compute the dynamical states. So it means that we compute the surface density of solids, the inclination and the eccentricity of solids, and their composition as a function of time and location in the disk. We compute the accretion of solids using rate equations, which are based on the Safronov approach, but modified later on by Greenswag-Lissauer and Ida and Makino. Then in terms of the structure of a planetary envelope, which is important in order to compute the accretion rate of gas, we solve the 1D radially symmetric structure equation for planets. So these are equations similar actually to stellar structure equations, but modified for the case of planets. So this is similar to Bodenheimer and Pollack papers. Then the outer boundary condition for the gas envelope structure can occurs in 3 different regimes. The first regime is the attached regime, when this is the beginning of the formation of a planet, when the mass, when the radius of a planet extends up to the Hill radius. And so there is some contact between the protoplanetary disk and the surface of the planet, the outer radius of the planet. And this attached phase lasts until the gas accretion rate that is required for the planet is larger than what can be given by the disk. And then at this point, there is not any more contact between the outer boundary of the planet and the disk. And we enter in what is called the detached phase. And then this detached phase lasts until the planet so disk has disappeared, and then we enter in the isolated phase where there is only the planet that evolves due to cooling. We also include the entire structure and radius of a solid core using a modified polytropic equation of state from Seeger et al. Migration is included in type 1 and type 2, and we have a full n-body interaction between planets, which leads to maybe scattering of planet collisions and maybe capture in mid-motion resonance. We also include the fact that the star evolves with time, and the stellar evolution model are the one of Barrett et al. 2015. So stellar evolution is important because, for example, this changes the irradiation of a star onto the disk. Then we also include the tidal evolution of planet, assuming a constant Q factor, but this is done only during the late evolution phase of the planet. So during the few billion years, we can't change the supermajor axis of planets due to tidal evolution. And then also during the evolution phase, we take into account atmospheric escape for closing planets, and then we have a semi-empirical model for the bloating, so the increase of the radius of a planet. So again, this is a quite complicated model that is actually very well described in the paper by Yann Alibert et al., which is in review but already available on the archive. So let's give some examples. So just on a few examples of what we compute. So I've here taken just a few parts of a model on the disk evolution for the gas and the solid on the top, then the entire structure of the planet and the migration of the planet. So on the top left, you have an example of the evolution of, so this is for a typical simulation where we have evolution of a protoplanetary disk. So you see on the, you see the evolution of the surface density as a function of time. So the different curves are for different times that is shown as a color code in million years. And so we have, for each curve, we have the evolution of the surface density as a function of the location in the disk. And you see that we have here a disk with an inner radius that is a little bit smaller than 0.1 AU, and the disk extends at the beginning up to a few hundred AUs. So, okay, this is the evolution of the surface density of a gas surface density in the disk, which result from the alpha viscosity and photoevaporation onto the disk. Then we have the evolution of, on the other panel, the evolution of a mid-plane temperature in the disk as a function of time, so of the same times, and you see that basically the disk cools down as a function of time. Then on the top right panel, you have the evolution now of the surface density of solids in the same disk. And okay, this is a little bit difficult to read. I've not, so actually the color code is the same as on the other panel. So for the gas, so this just gives you the evolution of the surface density as a function of time and location of the solids. And then you see that in these, there are many planets that form and accrete some solids in this disk. And so the number that you see, they give you the final mass of a planet. And you see that in this system, we will end up with a planet that is very massive. So 1,700 Earth masses, so very big giant planet. And then at the location, and so this is a formation, in situ formation. So just to ease the visualization here. And so at each location of a planet, you see that there is, you have, as a function of time, less and less solids, just because the solids are accreted by the forming planets. So this is particularly visible for the big planet that is located around 10 AU, where you see that at the beginning we have a surface density of solid around 10 or a few grams per square centimeter, and as time goes, you see that this surface density decreases just because the solids, they are accreted or ejected by the forming planets. So this is for the disk of solids. Now, if we look at the internal structure of a typical planet, so again, so these are internal structure profile of a planet. So you have a pressure in log as a function of the temperature also in log. So the inner part of a planet is on the bottom right corner of each diagram, and the surface is on the other side, so on the top left corner. So we have the different phases that I mentioned before: the attached phase, the transition phase, the detached phase, and the evolution. Okay, so the first phase, the attached phase, is so you see that we have, as a function of time that is in the color code, we have a change in the pressure temperature profile as a function of time, and basically as the planet accretes mass, then the inner temperature is going up, and the inner pressure is also going up. So you see that the end of a curve on the lower right side of a curve is going toward higher pressure and higher temperature. This is just because here we have more and more gas in the planet, and so the pressure at the center of the planet and the temperature increases. Then the transition phase is just a phase when we go from the planet start to detach from the disk. So this signals the time when the amount of gas accretion that is required by the planet in order to fill its Roche lobe is larger than one can be given by the disk. Then we have detached phase, where we have evolution, and then again the planet cools down, but as it's well known, cooling down for a planet means increasing the central temperature and pressure, actually more pressure here, just because of contraction. And then we have the evolution phase that we see here on the last panel. Finally, on the bottom right panel, we have a migration map. So this is just a computation where we have the migration rate in year -1 as a function of the mass of a planet and the distance. So this is at a given time in the disk history. And so basically, red means here outward migration, and blue means inward migration. Okay, so now let's look at one typical disk and one typical planetary system. So this is a system where we started the formation with 100 planetary embryos that are between so they are between the inner boundary of the disk and the outer boundary. And so we have here 4 snapshots where we have in all of them the mass of planets as a function of the semi-major axis. So the first panel shows the status of the disk at 10 to 5 years, so really at the beginning. And then we have here all planets that have started accreted solids. And so this is basically in situ accretion of planetesimals. So you see that the lines are vertical. So this is just in situ accretion of planetesimals. Then around 1 million years, then we start to have migration, and the system start to be in resonance. And the color code that you see here is the ratio of a migration to the growth time scale. So basically, bluish means that you have more or less in situ growth because migration is small, and reddish colors means the opposite, that you have more rapid migration than growth. Then in the third panel at 3 million years, we have still migration in resonance, and we start to have some giant impacts. So you see the giant impacts. For example, for a planet that is at 0.15 AU at a mass around 0.2 Earth masses, you have a vertical line that you see, and at the same time, you have a planet that is depicted with an empty circle. So empty circle planets are planets that are lost in the system, so meaning that they have been collided with another planet. And then finally, at 210 to 7 years, we have giant impacts And this is after the gas disk has disappeared, and because there is not any more gas disk, then the planets start to acquire some eccentricity and inclination, and this triggers some impact inside the planetary system. So now, if we look in more detail at the same system, but we look now at the evolution of the submajor axis of the planets as a function of time, then as a color code, you have the mass of the planet. So you see that at the beginning, all the lines are horizontal because that's in situ formation. And then at some point, you start to have some interaction between planets. And then at so at 5 million years, which is the lifetime of the disk, you see that the gas disk disappeared, and then this triggers the instability. So you don't have any more damping of eccentricity of planets, and then they start to collide with themselves. Now, from the same system, if I look at now with the same diagram, but the color code now is the surface density of gas. So again, you see at 5 million years, the gas disappears, and then you see that it's really at this time when the gas surface density starts to be very small, that you have you start to have this instability and many collision between planets. So now, if we look at the end state of this planet formation for this specific state, so this is the end state of a model in the mass versus submajor axis diagram, and so you see that we have we started with 100 planetary embryos, but at the end we just have around 20 planets that survived. The green planets, they denote dry planets, and in this case, the gas fraction is less than 10%. For the planets that are depicted in blue, we have two symbols. We have the circles that are icy planets with a fraction of gas larger than 10% in mass, and crosses are icy planets with a fraction of gas that is less than 10% in mass. And in gray, you have all the lost planets. So you see that it's quite a number of them. And the numbers that you see on the top are the metallicity. So this is a metal poor system. The mass of a gas in solar masses in the disk at the beginning, and the mass of solids in Earth masses at the beginning. So this is one typical example of a planet. Now, what we want to look at is, okay, now if we know that there is a very wide variety of typical disk, and so that protoplanetary disks, they have different composition, different lifetime, and different masses. And then what we want to know is, okay, if we take all this diversity of protoplanetary disks, what do we expect in terms of the population of planets that are formed? So what we will do basically is to run planet formation models similar to the one I've just showed before. So we will compute formation of planetary systems, but each time changing the properties of the disk. So its lifetime, its composition, and its mass basically. So what I will show here is a movie where I will show you the evolution of the formation of 1,000 planetary systems. So we have, so for each of these systems, we start with a different protoplanetary disk with different mass, different time scale, and different composition. For all these disks, the star is assumed to be solar. And then for all these disks, we will assume that there are 100 planetary embryos that are present at the beginnings. And so the mass of these planetary embryos is the mass of the moon, so 0.01, 10 minus 2 Earth masses. So actually you don't see them on this diagram because this diagram starts at 0.1 Earth masses. Okay, so we start with 100 embryo of 10 minus 2 Earth masses, and then they will grow, interact, accrete solids, and maybe gas at some point. So then I will start the movie. So you see that we have kind of a wave. So again, these are 1,000 planetary systems. So all these planets, of course, they are not in the same protoplanetary disk. So now in terms of the colors and the symbols, so the crosses are in black are the solar system planet, just to guide the eye. In red, you will have the gas-dominated planets, which are in general massive. In green, as we said before, you have the dry planets. So there is no ice accreted during this formation process for these planets. And then in blue, we have the planets with some ices, some volatiles. And in gray, you have all the lost planets. So you see that some of them have been lost inside the disk, and you see that there is a lot of planets that are lost on the vertical line on the left, which are these are planets that are just lost. They cross the inner boundary of the disk, and then they end up in the star. And then finally, the horizontal line that you see for some of the planets, or actually for all of them, they gives you a notion of the eccentricity of this planet. And you see that these eccentricities start to appear in the late times, because you need to have massive enough planet to excite the eccentricity of the planets. And so at the beginning, the eccentricities are small, and then they start to be very large. And you have a time that is shown on the top. So something that is important to know is that, okay, there are different kind of population synthesis model that you can find in the literature. And so the one that is here, as I've shown before, is based on what we call first principle models, and they are not optimized trying to match the observation. And actually, the only I would say completely free parameter that we have here, and which is kind of optimized to some sort, is the size of planetesimals. So we have planetesimals that are around a few hundred meters in size, so quite small planetesimals. Okay, so now this is the evolution of so these are the formation of 1,000 planetary systems. So now what is something that is important is to try to understand what is the effect of a number of planetary embryos that we put at the beginning in a given protoplanetary disk. Because, I mean, we assume in the previous movie that we had 100 embryos, but actually this is something that is arbitrary. So what we have done here in these 4 diagrams is to change the number of embryos, planetary embryos we put at the beginning. And so just, yeah, the location of these planetary embryos is random, and we assume that the probability to have a given starting location of the embryo is uniform in log. So basically, there are more embryos that start inside than outside, because this is uniform in log. So you see here, we have different, so 4 different calculations from 10 to 100 embryos. And something that is very interesting is that we see that obviously the eccentricity of the planets increases when we have more dynamics in the system. So this is clear comparing the 10 embryos with the 100 embryos. Something that is also interesting is that if you look at the planets that are low mass below the Earth and dry, so green ones, you see that there are less such planets in the 100 embryo case compared to the 10 embryo case. And the reason is that when you have 100 embryos, the collision between planets in this low mass regime are quite important. And then the planets in the inside of the system, they grow by mutual collision of protoplanets. And in a way that is reminiscent of what we think happens for the inner solar system, for formation of the inner planets in the solar system. So just to give another magnitude, so these are quite heavy and intensive numerical calculation. Here, it takes around, roughly speaking, 1 million CPU hours per population for the 100 embryo case. So this is quite a big computer time that we have to invest in order to have these models. Now, if we look at the end state, so what is basically, this is the end state of the movie I showed before. So what is interesting is to try to compare the different subpopulation of planets we have with what we know from exoplanets. So on the left, you have the result that was shown in a paper from Gaudi et al. In 2020, where we see that we have different classes of planets in the mass versus period diagram. So we have hot Jupiters on the left, and then close-in low-mass planets that are around 10 days period or 10-ish day period. Then we have a planetary desert with not a lot of planets around between 10 and 100 Earth masses, cold Jupiters, and so on, and then distant super Jupiters. And on this diagram, the different colors reflect the different method for discovering these planets, and where you see a strong effect of the observational bias. Now, if we compare on the simulation, actually, what is interesting is that we see a lot of similarities. In particular, we can see the close-in low mass planets, and what is interesting is that we see that according to the simulation, they could be split actually in two subclasses: the dry planets for low masses up to a few Earth masses, and then the wet planets from a few Earth masses up to a few tenths of Earth masses. We also have the cold Jupiters, the distant Jupiters, and then there is a whole population of icy worlds that are not known from the observation, just because it's very difficult to observe them. Something that is interesting is that there are not a lot of hot Jupiters. In particular, there are not very hot Jupiters in the simulations. But there is something that is very important to keep in mind on the plot from Gaudi et al. This is a plot that has not been debiased. So, and we know that hot Jupiters are extremely much more easy to observe and to discover than other planets. And all the hot Jupiters that we see on the diagram, actually, if you correct from the observational bias, they just represent 0.5% of all the planets, which is something that is very difficult to see on the diagram because it includes the observational bias. So now on the simulation, we don't have very hot Jupiters, and we have only a few mildly hot Jupiters. So this can be this could originate from two effects. Maybe this is a statistical effect because we don't have enough simulations, and we have only 1,000 systems, and so maybe that's not enough, and that's the reason. But maybe another reason is that hot Jupiter system may be formed by some processes that are not in the model. In particular, if the hot Jupiters they are brought too close to the star in the late evolution due to tidal interaction with the star in a way that is more complex than the one that we do here, then maybe that could explain why they are not in the model. But this is something that I would say is not settled, and we are working on to try to understand this difference. Now, what I would like to do is to have a look at the different kind of architecture of planetary system that we have in the model. So I have here a gallery of some planetary systems, and so I will just show you a few of them. So the first one that is highlighted here is the solar system, just for comparison. Okay, and so now if we look at this system, we see that it's interesting. It looks very regular. So there is a very high degree of similarity between the masses of the planets, one close to each other. So we have a lot of correlation. Then if we look at this system here, it looks quite different from the one just before, because you see that the inner planets, they are not dry, but now they are wet. Okay, they are depicted in blue and not in grid as one before. So it looks here that all planets, they are wet. Now, if we look at another system, this one, you see something that we may look like a little bit like the solar system, except that it's a little bit more compact, where we have inner planets where we have two dry planets and two wet planets, and then outer planets that are wet, and two giants in the middle. So that's a system where we have, I would say, the three main classes of planets: dry, wet, and gas giant. And then finally, we have this system here, where we have at the end only one planet left, which is a giant, which is in the outer part of the system, and all the others in gray, they have been ejected. And by the way, the number that you see here is a metallicity. So, for example, this system is a metal-rich system. Okay, so from that we can distinguish, define four classes of system. Class that I've chosen before: class 1, Earth and ice worlds; class 2, migrated subneptunes; class 3, mixed system; and class 4, massive giants. So let's have a look at the first class, the Earth and ice world. So these are some examples of these systems. So now the numbers that you see for each panel are the metallicity, the mass of gas in solar masses, and the mass of solids in Earth masses. And you see that it's interesting because if you just try to fit more or less the mass of the planet as a function of the semi-major axis, you have two power laws increasing mass up to around a few AU and then decreases a mass that decreases as a function of semi-major axis in the outer part of the system. Okay. Okay, so now if we look at, if we analyze this system, what's interesting is that we have only low mass planets. There is, if we look at, you analyze the formation of the system, there is some migration for the outer planets. The planets are rocky inside and icy outside, and so we keep the compositional ordering, so there is no mixing in this compositional split. The masses are typically between 1 and 10 Earth masses, but closer to 1. And the mass, as we said before, first increases, then it decreases with distance, and they have in general low eccentricities, except for very, very small planets. Maybe, but it's difficult to see because statistic is not very large. We have the innermost planet in general has a higher eccentricity. We have a high number of planets, 5 to 10 larger than 1 Earth masses. And in terms of initial condition, we'll come back later, they in general are formed in low mass disk with low metallicity. And then basically how they form is their formation is dominated by local solid growth with some migration, but not very large, and some impacts between planets. Now the second class are migrated, some Neptunes. So again, you have some examples here. And so you see like in general, we may have a few dry planets, but in general planets, they are wet. So, and in general, the mass looks like it is, well, more or less independent on the distance or slightly decreasing with the distance. So we have, in this case, we have only low mass planets, but then there is a strong migration. And for example, the fact that we have wet planets very close to a star is because there is migration. The masses are a little bit larger than class 1, 3 to 20, but around rather around 10 Earth masses. Nearly all planets are rich in volatiles, and as we said, the mass is a little bit decreasing or flat with distance. They have low eccentricity as a class 1, except for the minor bodies, and there is a lot of planets, 10 to 20. And in terms of initial condition, they are forming intermediate mass disk, and they have a widespread in metallicity. And so basically, in terms of the formation of the system, they form with significant type 1 migration. Then there is generally resonant convoy that is formed, and then you have some instabilities. Class 3 mixed systems. So we have here some examples again. So what is interesting here is that this may be the one that looks the most like the solar system. With some giants in the middle of the system, I would say, around a few AU, and some planets that are either ice-rich or ice-poor inside, and some planets ice-poor outside. So, okay, typically there are 1 or 2 giant planets. They are not very eccentric, and they don't have a very, very large mass. So if you look back here, you see that, okay, there are a few Jupiter masses, but in general, they are not so massive. There are 1 or several inner low mass planets that can be rocky or icy, and then the outer planets are icy. There are not a lot of low mass planets, around 1 to 10 larger than 1 Earth mass. And in terms of the initial condition, there is a medium to high solid content and widespread in metallicity. And then in terms of formation, then this system have not so big giant planets, so they don't disturb everything, so there are no violent instabilities in the system. Finally, the last class 4, is the one where we have massive giants. So you have a few that are shown here. So now, in terms of how they are, so in general, there are only giant planets plus, and usually very massive, plus maybe some leftover things that could remind us the Kuiper belt, although they are more massive in the system. The giants, they have high eccentricities. There are a low number of planets, 1 or 2 typically. And in terms of initial conditions, they are formed in massive disk, long-lived with high metallicity. And so in terms of their formation process, what happens in these systems is that there are several massive giant planets that are formed, typically 3 to 4. But then because of their large masses, then there is some dynamical instabilities, and then all the lower masses are destroyed. And in general, only one, maybe two of the massive giants are preserved. The other one, they are lost by dynamical instability. So now what is interesting is to try to have a look at, try to have a synthetic view at these systems. And the question is what sets this outcome between class 1, 2, 3, 4. So what we have done here was to plot the total mass of a system in Earth masses as a function of the initial mass in solids. And then the color code will tells you what is the number of planets with masses larger than 1 Earth masses. Okay, and you see that there are some clear trends, and basically we see that it seems that there are 2 branches, one lower branch and one upper branch with some transition region, and then there is a gradient of in the colors, so not a lot of planets at the very low initial mass in solids, and it grows up to in the middle on the first branch, the lower branch, and then when we go on the higher branch, then we in general have some much less planets, with this number decreasing when we go to higher initial masses in solids. So now, if we look at the 4 classes, these are where we can see the 4 classes. So the first class are for mass in solids up to 100 Earth masses. Then we have the class 2, so the migrated Neptunes. Then we have a mixed system that are in between the 2 branches. And then we have the class 4, the massive giants that are in on the upper branch. So now to finish, the last part I want to address in this lecture is how we can compare the models with the observations. So we had already some comparison with in terms of the different classes of planets, but now we want to go deeper and try to compare with some quantitatively with some surveys. So the first thing that we'll do is to compare with the ARPS GTO survey. So the ARPS GTO survey, we have 161 planets that are around 102 stars. And so the multiplicity is 1.6. That's just a ratio of these 2 numbers. And so what you have in this diagram is the efficiency of the observation as a function of mass and period. And then on now, if we look at the synthetic planets, so if we now include the observational bias, because we have to, then in black you have a synthetic planets, and then in red you have a HARPS planets. And so the first thing that is interesting is that you see that this is quite the same shape. Now, if we look at the numbers in the synthetic planets, so if we start with the same number of stars that have been observed by HARPS, then we have 317 planets with a number of stars with planets that is 2 or 4. And so we have more planets, basically a factor 2, but the multiplicity is very similar. We can see the different kind of planets that are on this diagram, but we also discussed that, already discussed that previously. So what is interesting is that in terms of agreement, the global structure and the relative distribution of different kind of planets is similar, and the mean multiplicity between the 2 is similar, which is very interesting. Now, in terms of disagreement, the model predicts by a factor 2 the absolute number of planets. So the question is, maybe this is due to the initial conditions, and maybe some disk, for some reason that we don't really know, they don't have initial planetary embryos for some reasons. Maybe there is some differences in the assumption we have regarding the initial disk lifetime and disk masses to what is formed. For example, we know that stars form in clusters, and then maybe some disks are destroyed very rapidly by EUV, or maybe there is some dynamical stripping of the disk and later on the planets because of the star environment. Also, something that we mentioned before, the Jupiters, they are too far out and there are too few compared to what is observed. And so, and as I said already before, maybe this is due to the fact that in this model there is only this migration, and we don't have scattering and quasi plus tidal sterilization mechanism that could form hot Jupiters. Now, if we look at the planetary mass function, so Okay, so we have on the left the histogram of the synthetic planets in black. In blue, the scale synthetic, so we just divided by factor 2 just to have the same number as in harps, and then in harps is in red. So on the left, that's the histogram, and on the right, that's the cumulative distribution of masses. So what we see is that we have a bimodal structure of planetary masses that is observed in harps, which is quite good. There is a change of slope at 20 Earth masses that we see on the cumulative distribution, and so this is the result of the core accretion mechanism, where we have fast runaway gas accretion beyond the critical core mass. And critical core mass, I said at the very beginning, is of the order of 10 Earth masses. So now, and at this critical core mass, the mass of core is similar to the mass of the envelope. So we expect that we have a change of slope at 20 Earth masses. What is not good enough is we don't have enough intermediate mass planets by factor 2. And then the giant planets, they are more massive than observed. So you see that the histogram is shifted toward more massive planets. So this is this results probably to a too fast gas accretion. And so and maybe some hints. What could be missing here is that we don't include 3D circulation as in the paper of Sulagi et al. And maybe a low viscous disk, lower viscosity disk would lead to smaller gas accretion. Now, the other very interesting survey to compare with is the Kepler survey. So on this diagram, you have the result of the Kepler survey. So now that's planetary radius versus orbital period. And then the number gives the occurrence rate, so number of planets in the area divided by the number of stars. So now if we look at the synthetic formation model, so I will just look at the one which is labeled Baird N100, which is the population with 100 planetary embryos. And so where you can see the same regions that have been depicted here on the diagram. So what we can see is that there is quite a good agreement in terms of, and here we have decreased the number of planets by here factor 5 actually, which is interesting because you remember that in the case of harps we had to decrease by a factor 2, but here if we want to have the correct number we need to decrease by a factor 5, and it's not exactly clear why we have this difference. Okay, so now, but if you look at the occurrence, the relative occurrence of different subpopulations, you see that except for the sub-Neptunes between 2 to 4 Earth radii, then the numbers, the fraction of planets looks similar to the observations. But as I said before, the absolute occurrence is too large. We have 5 times too many planets in the synthesis. And finally, the radius valley, so the difference, so the fact that we don't have many planets observed in the Kepler statistics that are at intermediate radii is visible for single and 20 embryos, but not really for 50 and 100 planetary embryos. Final comparison with Kepler is to look at the period ratio distribution of the adjacent pairs. So on this diagram, you have so the distribution of period ratio from Kepler at the bottom in red, and then we have a distribution of period ratio for 20, 50, and 100 planetary embryos. And the vertical lines show the mean motion resonance. So you see that there are some system in mean motion resonance. Now, if we look at the same data, but looking at the cumulative distribution, we have on this diagram, again, the paired ratio of the outer to inner planet. And then this is the cumulative distribution. So in red, again, Kepler, and then the different model, 20, 50, and 100 planetary seeds. So what is interesting is that the higher the number of embryos, the closer the overall distribution to the observation. If you look at the violet versus red curve, and this is because of the increased dynamical interactions. And what is interesting is that migration does not lead to two compact systems because globally the shape is very similar to one of Kepler. But the disagreement is that we have too many planets in mean motion resonance. So this is very visible for 20 and 50 seed embryos, but still for 100 seed cores, where you see that we have a lot, for example, of system in 2-to-1 resonance. One reason may be that there is no dissipative process between planets that is included in this, and also no dissipative process that would be mediated by the disk. So time to conclude. So okay, so what I've shown are some end-to-end planetesimal based formation models. So what we have seen is that these models that can predict a quite wide diversity of architectures in planetary systems. We have seen that there is a fair agreement with the observed planetary mass function and a fair agreement in terms of the system compactness, what we have seen just before. Now, these models, they have some difficulties to explain a few things, in particular, the existence of massive planets at large periods, also the existence of hot Jupiters, at least a fraction of hot Jupiters, and also the relative rarity of systems in mean motion resonances. So these are two things that are not well reproduced in the models. I mean, there are some more, but these are probably the two most important ones. So conclusion, I mean, probably additional physical processes have to be included in these models. I've cited a few of them during the talk, but probably some of them have to be included to have some future generation of end-to-end formation models that would also be able to reproduce the things that are not well reproduced at this time. So I will stop now. So, and I will just stop sharing here. So, so in my time frame, we have a question. We have some questions in 1 week, but I think for you, questions are tomorrow. So see you tomorrow for the questions, and have fun watching the lectures, this one and the others. See you tomorrow.